All right, you guys. So for this third one, we have that the running time, okay, running time in T minutes of 200 family movies are recorded in the following table. Now let's take a moment and look at this table. So here we have a frequency, and also take a good look. We have these symbols here, right? And so these symbols here means that all of these are different intervals. For example, on this first one, you know that you have 11 family movies, 11 family movies between a T between 70 and 80. So there's 11 family movies that have a running time between 70 and 80. There's 47 family movies that have a running time between 90 and 95. Okay? And so that's basically what this table is telling you, right? Now I'm going to say something right away. Example up here, they tell you that this first interval, you have 11 of them, see? You have no idea how that's spread out, right? Because maybe of those 11, you have, I don't know, like 570s, right? So maybe 570s and maybe 673s, right? It can be something like that. Or you can have, you can have, I don't know, 270s, 271s, and whatever, 179, and maybe 675s, okay? Like times 1, times 6, times 2, times 2, okay? And so you have no idea how it is spread out within that interval, see? And so this is going to be relevant down the road for estimating means and stuff like that, okay? But we just need to understand that when we have intervals, we have to treat it like so, okay? And so for part A, part I, we need to write down the mid-interval value, interesting, of 70 to 80. So this first guy here, right? Now, the mid-interval value, following its name, mid for middle, and interval for middle of the interval. So what is the middle of the interval between 70 and 80? The middle between 70 and 80 is 75. Literally. For part A, part I, you are going to put 75 minutes. If you're stressed about showing your work, you can write 70 plus 80 divided by 2. That gives you the 75. Okay? So, yeah, that's part A, part I. Part A, part double I, and remember, anytime you have like I or double I, it means they're associated with each other, right? So for double I, we need to calculate an estimate, interesting, an estimate of the mean running time of the 200 movies. And so when we see the word mean, okay, let's just recall that mean is the same as average, okay? And what we're used to doing for average is saying like, I don't know, 70 plus 71 plus 71 divided by 3, right? And so you have your, notice, exact values, and you divide by your total. So if my data is 70, 71, 71, and I say find the mean of this, you take your exact values, you add them, and you divide by the total. When you have intervals, you don't have exact values. And so how do you do it? Well, part A, part I asks you to find a mid-interval. Ah, okay. So the mid-interval is something we need to use in this context to find the mean. Okay, so yes, I don't have exact values, but then what can I do? Well, your values are going to be the mid-intervals, okay? And so now I'm going to go ahead and add an extra column, just to be very clear, that says mid-interval. All right, and so from here, I'm going to make it very nice and pretty, although my artistic skills, you know, they're all right. Here it is. So here's my extra column that I just added. And so the mid-interval for this first one is going to be 75. The mid-interval for this second one is going to be 82.5, right? Because the middle of these two is 82.5. Remember, you can do 80 plus 85, so it's this plus this, divided by 2, gives you that 82.5. And so you can keep going and fill it all in, right? This is 87.5, this is 92.5, and this last one, careful, this last one is 100. And so here's a small detail you need to notice. You might have thought it would be 97.5, but think about it this way. The spread from 70 to 80 is 10. It's plus 10. From this to this is plus 5. Here's plus 5, here's plus 5, and this again goes to plus 10, okay? So if you're scared about falling into that little trap, right, you can always just add them both, divide by 2. Oops, make sure you divide by 2 at the very end, or else you end up with something a little different, because you would be doing 85 divided by 2. See? Happens to anyone. Anyways, this is a way that you can just always like double check, get the correct mid interval, whatever. The first time I tried this exercise, I got it wrong because I put a 97.5 here. See? It happens to anyone. I'm just pointing it out. Careful what the difference is from one to the next. Okay? Yeah. Anyways, so now I have the mid intervals all written down, right? And so from here, for calculating the mean, it works like this. I'm going to put all my mid intervals in pink in my formula so that it's easier to follow. And I'm going to put all my frequencies in green. All right, so frequencies will be in green. And so technically for your mean, you don't have the exact values, but you have frequency and you have mid-interval. So how do you do it? You say for this first one, okay, for this first one, you would say 75 times 11 plus, for the second one, 82.5 times 51. So basically you're doing the mid-interval. So for the third one, it would be the mid-interval times its corresponding frequency. For this fourth one, it's the mid-interval times its corresponding frequency. And for this last one, it's the mid-interval times its corresponding frequency. And all of this has to be divided by your total because we're talking about mean, right? And so divided by your total, well, what's my total? 200 family movies. What's another way to check your total? Add all the frequencies. And so you can add all the frequencies, and that has to be your total. And surprise, it's going to be 200. All right, so it's 200 by context, but you can also get 200 by adding the frequencies, okay? All right, cool. And so here we divide by 200, and that will be my estimated mean. Why is it estimated? Because you don't have exact values. Well, that's fine. You can still get a mean. It's just estimated. See? So let's do a little bit of color coding so that we're on the same page. So these are my frequencies, correct? And these are my mid-intervals, all right? And the 200 is my total, which is sum of frequencies or just by context, all right? Anyways, I put all of this into my calculator. So I'm going to do alpha y equals, press the first one, so I can put a fraction. And here, well, I'm plugging in for like half a year, but it works, see? Technically, you can put it into one var stats, use like a frequency list and stuff like that. But I'll just show it like this, all right? I think it's a little bit more intuitively easy to follow if I show it like this. But yes, you can go into one var stats. Anyways, divide by 200, bada bim, bada boom. There you go. And so for part A double I, we have that the mean estimated, right, is going to be 88.15 minutes, right? If you're the kind of person that loves significant figures, you can count 1, 2, 3, round it up or keep it the same. You round it up. okay? Both of them work. I suggest leaving the long answer. Then we have that this table is used to create the following cumulative frequency graph. And so cumulative frequency, as it says or as you read it, for example, a cumulative frequency over here at 75, right, means that here is your 75th movie. So notice how the total is 200. So movie number 200 has that amount of running time, right? And so notice how this curve looks. They organized all the movies from the lowest running time to the highest running time. So for example, the first or like the 10th or whatever, a movie has a running time of, I don't know, like 77, okay? And so that is how you read this graph. And so now that you understand how to read the graph, everything is a lot more friendly. The cumulative frequency curve, damn, they ask us to use the cumulative frequency curve to estimate the interquartile range. And so interquartile range, you're probably thinking, I think I know what that is, right? And so you're going to go ahead and open up your formula booklet, which is right there. And so over here, you've heard about interquartile range. It's a buzzword you've identified before. And so you look it up and say interquartile range, and there it is. Q3 minus Q1. Now, we need to understand what the heck is Q3 and what the heck is Q1. So, Q3 makes reference to quart, all right? So you can think about it as quartile 3 minus quartile 1, all right? Now, this has to do also with percentiles, all right? So I'm going to talk a little bit about this. And so when you have percentiles, for example, they say you're, I don't know, 70th percentile, right? So that means in your data, it's your data that is right at 70% of it, okay? And the issue is that we're very used to thinking from 0 to 100, right? So your 70th percentile is person 70. But here you have 200. So here it's the 70th, but of 200 movies. So, okay, what's 70% of 200? How do you find it? You do 200 times 0.7. And so your 70th percentile is movie number 140. So if I actually go to movie 140, which would be, I don't know, around here, right? This would be my movie that is in my 70th percentile, okay? So that is how you find percentiles. Be very aware that that your total, okay, is going to help you find where your percentiles, where your quartiles are, okay? And so if we're talking about in terms of quartiles, so I just talked about percentiles. If I talk about in terms of quartiles, think about it this way. Your quartile 3 is your 75th percentile. And your quartile 1 is your 25th percentile. So because it's in quarts, right, it's like 1/4, 1/4, 1/4, right? And so your first quartile is your first fourth of your data. 1/4, how much is that? 0.25. Boom, 25th percentile. While your quartile 3 is these three guys. So it's 1/4 plus 1/4 plus 1/4, 0.75. Boom, 75th percentile, sorry. And what is even another way for you to understand it, when you look at a box and whiskers diagram, okay, whoops, when you look at a box and whisker diagram, right, it's always going to be, this is your min, this is Q1, this is your median, which is the same as Q2, okay? It's the guy at 50%, right? This is Q3, and this is your max. what is the cool thing about interquartile range is that from min to Q1, you have 25%. From Q1 to the median, you have 25%. From the median to the Q3, you have 25%. And from the Q3 to the max, you have another 25%. And all of this has to do because quartile 3 is your 75th, and your maximum is your 100th. So it's like the top 25%. Interesting. And so interquartile range, yes, it's your range, so it has to be like the biggest minus the smallest, but because it's interquartile, that means you're looking for the middle 50%. So interquartile range, what's cool about it is that it's the middle 50%. This is why people are interested in it in the first place. It helps you find the middle 50% and whatever. It can give you a better notion of how to interpret what you found out. All right, that was a lot of blah blah, but I think I cleared up a couple ideas that some of you may have had. And so if I go all the way back here, and when you estimate the interquartile range, okay, I'm considering Q3, I'm considering Q1. And so to find Q3, I take my total, 200, because 200 movies, right? And I want to find which value is at 75%. And so 200 times 0.75, boom, 150. And for Q1, I'm going to do this 200 times 0.25. And so which movie is at my 25th percentile, or which movie is at my quarter 1? 200 times 25, 50. So, all right, so Q3 has to be at 150, Q1 has to be at 50. So Q1 has to be at 50. So this guy here is going to be Q1, right? So notice Q1 is at 50. Think about it this way. Q1 is at 50. And so at 50, I have, it's probably just 84, right? Yeah, I would call this 84. So Q1 is 84, okay? So notice here, maybe I shouldn't have put equals at 150 or equals 50. It's your Q1 is at 150. I mean, your Q3 is at 150 and your Q1 is at 50, okay? And so at 50, I have 84. So my Q1 is going to be 84. And my Q3 is at 150. So at 150, I have, so if this is 91, that would be 91.5. So that's 91. Right next to it's going to be 91.5. So Q3 is going to be 91.5. So that means that your interquartile range is going to be 91.5 minus 84. Your IQR is 7.5 minutes. All right? So again, not that hard, but you do need to understand how to get Q1, how to get Q3. The cool thing about this graph is that it's kind of easy to read, right? And so this helps you find like your Q1, your Q2, your Q3, like the location, and then you just have to find its corresponding running time or whatever. See? Sometimes you gotta do it backwards, like what they give you here, and then finding where that is. Like, is this the 90th percent, the 100th percent? Like, how much would it be, right? But usually, my experience is the other way around. They basically tell you like who's at the 60th percentile, right? Actually, let's do that example. So, who or slash amount that is at 60th percentile, right? So this is another classic. I don't think it shows up on this paper, but you know, I think I should show you anyways. So they might ask you who or what amount is at the 60th percentile. So you're going to take your 200, you're going to times it by 0.60 for 60 percentile, right? 60th percentile, sorry. And so 120. So whoever is at 120, which would be, I don't know, around here, right? Whoever is at 120, that is the amount for your answer, okay? which would be a little less than 90. All right, 89, I think. So that's how you read this graph. I hope that at the end of this video, you just feel good about reading the graph. Okay, that's the most important part, really. All right. All right, and now for part C, they tell us that Star Feud, I'm not sure if I'm saying that right, is a movie in the dataset and its running time is 100 minutes. Use your answer to part B to estimate whether Star Feud's running time is an outlier for this data. See? And so we have a movie that its running time is 100. So it's right here. See? So that means it's within my data, right? It's within my data and it's in a pretty high percentile, and I'm still not sure which, right? But it's a pretty high percentile. Point is, yes, it's within my data, but it might be a number that's like a little too big and it might be considered an outlier. See? And so what is the mathematical proof for whether it's an outlier or not? I'm going to show you now. See? Now, part of this, all right, part of this has to do with part B. See? So part B, we needed to use the interquartile range, and part C needs something from part B. It's not always the case, but a lot of times it is. Actually, here it says use your answers from part B. See? And so, first of all, what is an outlier? See? An outlier is a value that is too big or too small, and it doesn't make sense that it would be here. For example, a movie that lasts, I don't know, 30 minutes would be like here. See? And as you can see, almost all of these movies start at 70. So it would be a little bit a little bit weird to have a movie that lasts 30. Or maybe they have Lord of the Rings in here and the movie lasts, I don't know, like 180 minutes. And that would be way out on this graph. That is probably an outlier, see? So we have the intuition that outliers are like way too big or way too small, okay? Now, what is the level that you accept, okay? It has to do with the boundary that you define. So think about it this way. Maybe you say anything beyond this is too big, or anything smaller than this is too small, okay? Now, how do you find those values? Well, these would be considered your upper bounds. So anything above that, you would like, you know, um, consider an outlier, or your lower bound. So anything lower than your lower bound is something you would consider an outlier. How do you calculate the outlier? It is awfully specific. It is not in your formula booklet, but it's easy and good points. So this is the kind of thing that you will have to memorize, but if it shows up in your test, I think it's easy points. See? And so here, notice how the running time is 100. There's more on the right side, so I only have to calculate the upper bound. I'm still going to show you how to do lower bound, but for now, let's only do upper bound. See? And so the equation for upper bound has to do with the interquartile range. So for upper bound, you will be doing, because it's on the upper bound, because you're more on this right side, you consider Q3. So on the one hand, you have to do Q3 plus because you're more on the right side, right? Plus because you're more on the right side. So Q3 plus 1.5 times IQR. This is your formula for upper bound. And as you would expect, for lower bound, instead of Q3, you use the quartile that is more on the left, so it would be Q1. And because you're going to the left, right, you would actually do negative. So it would be Q1 minus 1.5 IQR. So there you have figured out how to calculate the bounds. And this is something you should think about if you ever read Outlier. If you ever read Outlier, think about the bounds. Okay? That is a rule of thumb you can do. And this is what I mean when I talk about procedure. See? Read the buzzwords, and through that, figure out what to do. See? Anyways, so the formula for upper bound in this case, we're going to have, so upper bound for real this time, you have your Q3, which is this. So you have 91.5. And because it's upper, we will be adding, so plus the 1.5 times IQR. So IQR we said was 7.5. And so your upper bound ends up being, let's double check. So your upper bound ends up being 91.5 plus 1.5 times 7.5. That looks fine to me. So your upper bound is 102.75. So your upper bound, which I'm going to now put in black. Okay, so your upper bound is pretty much, so if this is 101, that means this is 102. It was 102.75. So it's like around here. See? So anything to the right of this would be considered an outlier, right? So for example, these movies here mathematically are considered outliers, all right? So this is your upper bound. So anything to the right is outliers. These guys are outliers, okay? But the movie at hand, Starfield, is 100 minutes. And so 100 minutes, we put it in red earlier. It's this guy here, right? 100 minutes is to the left of the upper bound. So you would say, blah, blah, blah. Estimate whether it's an outlier. So you would say, no, not outlier. So on the one hand, that gives you an answer point, right? But for your method, you're gonna, well, this is a method point one right here. And your strong justification, all right, like your reason or whatever, is that 102.75 is bigger than 100. So 102.75 is bigger than 100. So this is your reasoning point here. This is your method point for using the formula. And this is your answer for, stating the obvious, no, not an outlier. See? All right, guys. Those are your 3 points. Fairly easy. One of the formulas you just gotta memorize, not in your formula booklet. All right, let's keep going. So here we have that it is believed that the running times of family movies follow a normal distribution with mean 88 minutes and a standard deviation of 6.75 minutes. Now, before we keep going, standard deviation, I need you to associate it to spread. Okay, so a bigger standard deviation means that your data is much more spread out. Okay, and 88 minutes, and your mean, we can associate it to average. Okay, I just want to start off by saying that to make this a little bit more friendly. So on average, these movies last 88 minutes, and the spread from one to the other is usually 6.75 minutes. Okay, usually, right? And so like the movie next to it would be, I don't know, 82, right? And then the movie next to that would be 95, 94, so 88 plus this. Okay, whatever, man. Just have the idea that standard deviation is spread. Okay, let's stick to that for now. And then it gets funky because it is decided, for some reason, to perform a goodness of fit test. Now this symbol here is chi. So this is what they call chi-squared. Okay, so this chi-squared goodness of fit test on the data to determine whether this sample of 200 movies could have plausibly been drawn from an underlying distribution. All right, and so we need to write down the null and alternative hypotheses for the test. And so for now, all we need to do is the null and the alternative. And so from here, we have the intuition. So null, which is HO, is basically no effect, no change, right? While the alternative, which is H1, is that there is an effect, yes, change, all right? So always think about the null as like no, okay, no effect, and H1 as yes, yes, there is. And so here, what are they trying to determine? Careful, they're trying to determine whether the sample of 200 movies could have possibly been drawn from an underlying distribution. And so, whether it could have possibly been drawn, right? And so from here, what I suggest, okay, to do is that you can say that HO, right? So no effect, no change means that they were drawn from this, right? It's like they think it was drawn from this, it got drawn from this, that would be no effect, no change, okay? So the context of the problem matters a lot. So in this context, no effect or no change means that, yeah, they got drawn from a normal distribution, right? Why is it like that? Because that's what they consider. That is their assumption. So you can think about it that way as well. HO like keeps your assumption. HO keeps your assumption, right? And so your assumption is an assumption of no change from the current scenario. And the current scenario that they're saying is that it comes from a normal distribution. Okay? So I know that's a little bit weird, but stick to it. So null, or your HO, is no effect, no change, and that you keep your assumption. And so the assumption that they're doing is that this was drawn from a normal with this distribution, right? And so HO technically from here would be the running times of the movies can be modeled by normal 88 6.75 squared. Okay, this is the first big thing we have to say. All right, so HO is no effect, no change. Keeps your assumption. They're assuming a normal distribution, so it can be modeled, right? And for H1, all right, and I know that HO is usually like not whatever they're trying to say, but in this context, they sort of like throw it to you as a curveball. See, so because they say could have possibly been drawn, that is the assumption they're keeping. That is their status quo. Okay. Usually, the sort of tests that they do is that they're trying to see if like, oh, does this have an effect or not? See, this one is the distribution where it comes from. So the context matters a lot. I know I've given the hint that HO is whatever. It's like not what they say, right? Well, in this case, because it has to do with the distribution and where it comes from and all that stuff, we keep that assumption. See, I know that's weird, but I had to explain it a little bit because, well, it's how this exercise is. So context matters for that kind of stuff. Usually you can just say not HO. See, usually you say not, I mean not HO, but you say not what they propose, and it works for HO. In this case, logically it's different. All right, that was a long explanation. Maybe I could have made it shorter, but it is what it is. All right, for H1, think about it as opposite of H0. Okay, and so if H0 is that the running times of the movies can be modeled by the normal, if HO is the opposite, is that the running times of the movies can't be modeled by the normal. Yes, that small difference is all you need to do. H1 is opposite of HO. See? All right, so that is for part D. Then for part EI, we're going to find the value of A and the value of B. And so from here, well, we take a look at our graph, right? And we see what they propose. So for example, the running time, if you have t less than 80, the observed frequency is 11. So they had 11 movies that were less than 80, and its expected is 23.6, right? And so there's a way, using the information of each of these rows, to have it make sense in terms of expected frequency, right? And so this does have to do, once again, with the mid intervals, because you're filled with intervals, you work with expected values, with estimated values, with stuff like that, right? And so from here, you can think about it this way, right? Or actually more than the mid interval values, because this is a normal distribution, you gotta think about what are your tools for the normal distribution. You have what is called normal PDF, you have normal CDF, and you have inventory normal, which is like inverse normal. See? In this case, our main tool will be normal CDF. CDF, I need you to think about it as cumulative. So if you have a range of data, you can use normal CDF. Ah, here you have a range. So let's better try to understand how they got the 42.1. So once we understand how they got 42.1 on this example, finding A and B is going to be very easy. See? So how did they get that 42.1? Well, we can go to the calculator, and because it's a normal distribution, I can go to stat. Sorry, I can go to distribution. So second bars, distribution, and boom, there are my tools. So we said it's cumulative because we have an interval, basically. So normal CDF is for intervals as well. See, because it's cumulative, it's also for intervals, right? And so from here you can say, okay, so my lower can be 8. Actually, I did it earlier, lol. So your lower can be 80. Your upper is 85. So this is example in red. See, this symbol here, the U, is mean, and they give it to you right there. Okay. If I look for normal distribution here, do I have the normal distribution here? Maybe I don't. Oh well, that's mean. Well, anyways, when they give you values, for example, 88 and 6.75 squared, yeah, the normal distribution is mean, comma, variance, okay, or standard deviation squared. And so from here you can deduce, right, that the mean has to be 88 because it's the first number that shows up, and that the standard deviation has to be 6.75 because it's the 6.75 here, just that you get rid of the squared, right? So basically you know that this is this, right? And so to get this, you can do square root. This goes away with this goes away with this. Standard deviation is 6.75. So that's how we figured out standard deviation is 6.75. It's all given to you right there. See? All right, cool. And so here I can press paste once I fill in all of my information, and boom, I get 0.21. Now you guys might be thinking 0.21 sounds nothing like 42.1. But what did I just do? What I just did is that I went to my calculator and I said, yo, I have a normal distribution that has a mean of 88 and a standard deviation of 6.75. So from here to here, right, for example, from here it would be a mean plus a standard deviation, and from here it would be a mean minus a standard deviation, right? So your normal distribution looks like stuff like this. And so technically what I just did, if in the middle I have 88, and I'm looking for the guy in red, which is from 80 to 85, that means, okay, maybe around, I'm making it up, okay, but maybe around from here 80 to 85. That's what you're asking for, okay? And so if you put normal CDF with these values, and we got 0.21, this 0.21 is actually the area under the curve. So that means that this is 21%. That is what normal CDF just told me. And so the expected frequency between 80 and 85 is 21% of my data. Now, 21% of my data, what is my data? My data is the number of family movies. And so my number of family movies, as we saw way earlier, is 200. So 21% of 200, 200 times this amount, right, the 21. There you go, 42.07. So 42.07, I count 1, 2, 3, round it up or keep it the same, you round it up. So 42.1, that is how you get it, see? So you find the percent, you multiply by the amount of movies, which is 200, and you get it, see? So for this next one, now that we understood what's going on, it's way easier. So for this one, I can go to normal CDF, say, okay, so my lower is 85, my upper is 90, my mean and standard deviation haven't changed. Boom, I got this percent. So it's 28% between 85 and 90, right? So I can say 200 times that percent I just got, and that is for my value of A. So your value of A is going to be 57.6274. Okay? If you really like significant figures, you count 1, 2, 3. Round it up or keep it the same. Keep it the same. 57.6. And for B, over here, notice how it's a t above 95. And so this is a little bit weird because you might be thinking, okay, so I'm going to put a lower for 95, but what do I put for upper? Think about it this way. You have 95 over here, and your upper is infinity. So it's any value of t that is above or equal to 95. So that means it's from this 95 to the right for your whole curve, okay, wherever it ends. But you don't know where it ends, right? And so here, all you really have to do is put a very big number for upper, see? So if this is technically just infinity, for our intents and purposes, you can just put an extremely big number and it'll make sense, see? So if you put an extremely big number that says, okay, you're going to capture all this area here until 99999, your curve probably ends like there. And so you're going to be sure that you accounted for like the last sort of tail, see? That is the game plan. That is what we tell a calculator. Our upper is going to be incredibly big. You press paste, there it is. So from 95 until the end, it's around 15% of your data. And so you can take this, multiply by 200, and boom, your B value is 29.9718. And if you want to count significant figures, you say 1, 2, 3, round it up or down. Here you would round it up, so you actually end up with 30.0 for B. And that is for part E, part I. Now for part E, double I, we need to perform the test to a 5% significance level, okay, and clearly state the conclusion of the context, right? Now, which test are we doing? There was a buzzword way earlier that I didn't talk about much, which said chi-squared goodness of fit. And so right now, I need to open up my calculator and find chi-squared goodness of fit, see what it asks for, plug in, and solve from there, okay? And so technically, right now, I'm going to go to stat and test, because it's a test, right? And if I scroll a little bit, eventually, here it is, chi-squared goff. And so goodness of fit is for goff, see? Goodness of fit is goff, all right? So I press over here, and okay, it's asking for observed, it's asking for expected in my list, and DF. DF is probably the only weird thing that shows up for us, right? And DF is what they call degrees of freedom. And technically, it's really just the dimensions of your table, right? And so the table that I'm going to be putting is a bunch of lists, right? And so this list, how many guys does it, how many guys, how many numbers are you going to be putting? You're going to be putting 1, 2, 3, 4, 5. And so here you have 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5, yes. And so degrees of freedom, for our intents and purposes, for the IBAISL, degrees of freedom is going to be n minus 1, okay? I don't want to jump too much into it because it can get a little bit confusing. This is the kind of thing I will suggest that you just sort of memorize. And so df is going to be n minus 1. And so if my n was 5, my degrees of freedom here is going to be 4. All right? Why would it be just n minus 1? Because it is a table, right? It is just one list. If it were a more extended table, the calculation for df is a little bit harder because you need to consider rows and columns, and it gets a little bit messy. See? For us, we're just going to worry about, okay, it's only rows, because you're putting one list at a time. It's only rows, n minus 1. Okay, and for us, TBH, it's pretty much always going to be n minus 1, right? For other math levels, maybe it's different. For us, it's just always going to be n minus 1. So, all of that being said, over here, the df is going to be 4. And now for my lists, I'm going to put the observed and expected. Where did I put list again? I gotta go to stat, edit. Here are my lists. So I have the memory of a goldfish, which was expected, which was observed. Over here for the chi-squared goth, they tell us for the chi-squared goth, they tell us that okay, L1 is observed. See, so technically, if I go back here, observed is going to be L1, expected is going to be L2. All right. So okay, I go to my list. So L1 is observed, L2 is expected. Let's go ahead and plug in. So 11, 51, 68, 47, 23. And so the observed 11 has associated the expected 23.6. The observed 51 has the expected 42.1. The observed 68 has the expected A, which we said was 57.6. The expected 47 has observed 46.7. So that one is very similar. And for 23, we have B, which we said was 30. So now I can do the test, right? So now I can go to stat, test, chi-squared goth. Observed is list 1, yes. Expected is list 2, yes. DF, degrees of freedom, was n minus 1. I had 5 rows, so it's going to be 5 minus 1. Calculate. These are the values that I just got. And so my p-value, which is the most important one for concluding, right? So my p-value is going to be 0.016, 0.01646, whatever, 46. See, for significant figures, your p-value is going to be, you count after the zeros, you start counting. See, so from left to right, your first real numbers where you start counting. So it would be 1, 2, 3. So you round it up, or keep it the same. You round it up. So it would be 0.0165. That would be your p-value. Okay. So at a 5% significance level, do you reject or not the null hypotheses? From here, you have to compare the p-value to your significance level. What's the intuition of that? They are both percents. Okay, so you're comparing the 1.65% to the 5%. So 0.0165, is it more or less than 5%? So 5% is 0.05. How did I get that? I did 5 divided by 100. 5%, okay? Or as a decimal, whatever it's. Okay. So I'm comparing the 0.0165 to the 0.05. Which one is bigger? Clearly the significance level is bigger. And whenever the significance level, we're thinking about it this way, whenever the p-value is smaller than the significance level, or whenever the significance level is higher than the p-value, you will simply say that there is sufficient evidence to reject HO. And so basically here you will be rejecting HO, right? Reject HO because of that, right? And so you have 1 point for answer for saying that you reject HO. You have another point for reasoning, which is saying this. You have another point for process or answer of your degrees of freedom. And yeah, that's pretty much most of that exercise for this last part. See? If you want more intuition on why this would mean rejecting, remember how I said that they're both percents, right? And so if you have the significance level, if it's significance level at 5%, you are looking for a percent that is even smaller. And so think about it this way. Your benchmark is at 5%. Anything better than 5% means you reject HO. See? It means that your data is like good enough, right? Why is that the case? Because if you had a percent that was higher than the significance level, imagine I got 7 or 8, that means, okay, that the data you did or the test that you did tells you like, okay, you were good, but you're not good enough. See, so to be good enough, you gotta be lower than the threshold mark. You gotta be lower than that significance level. See, and so because we're talking about probabilities, right? If we're talking about a critical level, which is like an actual value, you gotta be beyond that benchmark. See, in this case, you want to be smaller than that percent. If you're still confused, I'm gonna do a quick drawing, and that will finish this video, or this part of the video at least. And so technically, if you have a 5% significance level, it means that this last 5%, all right, you want to be within that 5% to the right. See, if you get, I don't know, 7 or 8%, that means you're around here. See, and so notice how it's a bigger percent, so it's more likely to get green than purple. You want to like ask your data to be like very rigorous, to be better than 5%. See, so right now we actually got 1%. So we got 1%, which is barely there. See, so 1% is clearly better than 5% because it's harder to get. See, it's more rigorous. You're asking more of it. See, so because your p-value is less than significance level, it means you're farther to the right on the curve, and it means there is sufficient evidence to reject HO because you're farther out than what HO expected you to have. HO has a certain spread to it, a certain variance, and you were beyond that variance. And so if you were beyond that variance at a 1% level, at a 1%, sorry, then that means, yo, your HO, like, something's wrong. See? And so you reject HO. Remember that HO is the case of no change, right? Or no effect. So you're saying, no, there is an effect. See? You're wrong. You're wrong because I'm way farther out than what I should be. Okay? Being like in range means being in here. But at 1%, or better said, beyond this last 5% means, okay, you're like way out. See, you're way out. So, bada bing, bada boom, reject HO. Ladies and gentlemen, I was a little bit unclear in explaining part D, but I think everything else is pretty good for this video. If you have questions, leave them in the comments. Stay with the idea that the null is no effect, no change. All right? And intervals, yes, they're scary, but once you understand the mid thing, or that you can use cumulative, everything's a little bit more friendly. See? There's always ways to make exercises more friendly and problems in life in general. Ladies and gentlemen, I hope it helped. I'll see you around.